Welcome back to the Explainer. Today, we're kicking off part 1 of our look into metal-clad switchboard construction. We're opening the doors, literally, on the internal architecture of marine medium-voltage switchgear. Now, if you've ever stood in front of one of these massive steel cabinets down in a ship's engine room, you know they're the absolute beating heart of the vessel's power plant. But we're not just looking at the outside today. We're going deep inside a metal-clad cubicle to really understand its function, its core concept, and exactly how its internal geometry is engineered to stop a fault from becoming a total disaster. To really wrap our heads around how these systems protect a ship, I want you to imagine an apartment building. Think about a modern, well-built complex. If a fire breaks out in one unit, thick concrete walls guarantee that the blaze can't easily spread to the apartment next door, right? That physical barrier isolates the danger. Well, that's exactly what metal-clad construction does inside a switchboard cubicle. And that brings us to our first major takeaway. Inside these cubicles, metal walls equal fault firewalls. Metal-clad switchgear is built using rigid steel partitions that physically separate the different internal zones. So if a fault, like a massive, explosive arc flash, happens in one zone, it's completely physically isolated from the rest of the cabinet. Which leads to the golden rule of this design: one fault, one compartment, never the whole board. It's a structural philosophy that basically expects the worst to happen. It's designed so that a catastrophic fault can blow up in one specific area without taking down the entire switchboard. Because, if you lose the whole board, you're leaving the vessel completely dead in the water. Not exactly a good day at sea. So how do they actually pull off this fault containment in the real-world hardware? Well, every metal-clad board is built using 5 core compartments every single time. You've got the bus bar, the circuit breaker, the table terminal, the secondary equipment, and the operating unit. Let's do a quick step-by-step breakdown of this anatomy so you know exactly what's going on inside each of these isolated rooms.
First up, compartment number 1, the bus bar compartment, housing the copper bars.
Then we have number 2, the circuit breaker compartment, which holds the withdrawable breaker. Moving on to number 3, the cable terminal compartment, bringing in the cables and sensors. Number 4 is the secondary equipment, housing the protection relays up top. And rounding it out is number 5, the operating unit, for manual control and interlocking. Okay, so how do we actually apply this to technical sizing? Well, that main bus bar compartment we just mentioned, it is definitely not a one-size-fits-all situation. The industry uses a practice called bus bar scaling. This basically means that the number of physical copper bars and their actual cross-section scales directly with the rated current the board is built to handle. Simply put, more current means you absolutely need more physical copper to carry it so things don't overheat. Let me give you an example. A 1250 amp board is typically going to run 2 bus bars per phase. But if you step that design up to a 1600 amp reading, those 2 bars just won't cut it anymore. You physically have to have 3 bus bars per phase. The current literally dictates the amount of physical copper. So let's do a quick knowledge check here to see this in action. Imagine you're reviewing a spec sheet for a new vessel, or maybe you're out doing a physical inspection, and you look into that main compartment and count exactly 3 bus bars per phase. Based on the scaling rule we just talked about, what current rating does that physical setup suggest? If you said 1600, you hit the nail on the head. 1600 amps or higher. That extra copper bar isn't just for show, it's there for a very specific thermal reason, carrying that heavier current so the system doesn't overheat under load. Understanding this little detail lets you read the physical hardware almost like you're reading a blueprint. All right, let's quickly summarize our tour here. You now know exactly why metal-clad construction exists. It's all about fault containment using rigid metal firewalls. You know the 5 core compartments that make up the anatomy of every board out there, and you understand that the physical copper bus bars inside always scale up with the current. It's a brilliant architecture, and it's absolutely crucial for maritime safety. But, this leaves us with a pretty massive cliffhanger. We know these compartments are designed to contain a fault, but what actually happens when a violently explosive arc ignites inside one of these compartments, right behind a closed metal door, while an engineer is standing just inches away on the other side? What makes that situation survivable? Really think about that for a second, and I'll see you in part 2 of this explainer where we're going to unpack arc-proof safety and physical interlocks.